Hello and welcome to part 3 of this introduction to learning from unlabeled instructions. In this video, I will present how we can plan actions in order to learn faster. Let's start a quick reminder of the previous video. So in this toy example, we demonstrated the idea of assigning artificial labels for each task hypothesis. And we've seen that by repeating this process for quite some iterations, we can see that one hypothesis is more likely to explain the data than all the others. We have seen that by using this labeling method, we can find which hypothesis explain better the structure of the received data. We then explain how to measure this likelihood using only standard classification techniques, that by training a classifier for each hypothesis and comparing the final coherence of the classifier with the data. We then showed results from a pick-and-place experiment and a brain-computer interface applications, reporting results from online experiments. We finally observed that different action selection methods, such as random and epsilon greedy, can affect the performances of the algorithm. And the question was therefore, can we do better than this? Is there an optimal strategy? And that is the topic of this video. So what does planning mean in such learning problems? Planning is also often called active learning, which means that the robot is active in the process of learning the task. The robot wants to identify the correct task faster. It wants to reduce the uncertainty as fast as possible. And usually, in the kind of scenario we consider here, when the robot knows a set of possible tasks, we can see this problem as a lying oracle problem. Let me explain this. We can see each hypothesis as represented by an oracle that predicts what the user will say for a given action in a given state. As for each hypothesis, the prediction may differ. The goal of the robot is to find which oracle is telling the truth. To do so, the usual technique is to perform action for which most of the oracles disagree. By performing the action, we can receive the actual information from the teacher and discard the oracles that were wrong. So discarding the hypotheses that were wrong. So let's materialize this idea in a new toy problem. In this toy problem, the world is shaped as a T. There is only two hypotheses. Hypothesis 1 is the hypothesis that the teacher wants the robot to go on the left side of the T, and hypothesis 2, the hypothesis that the teacher wants the robot to go on the right side of the T, which are materialized by this dot at the edge of the T. As in the previous toy example, the instruction signals are two-dimensional and are represented in these two spaces with their associated labeled hallucinated labels, if you may. On the right side, you can see on the top the representation of the uncertainty in this map. And below is plotted the probability of each hypothesis. It compares the likelihood of each hypothesis classifier with their respective data. So in this example, the agent will start at the intersections and will try to reduce the uncertainty about the meaning of the instruction it will receive. So intuitively, we can understand that the robot will go left and right. So if we go left, he will expect from it hypothesis 1 a signal that means yes, because he is going in the directions of the goal. And for hypothesis 2, he will expect a signal that means wrong, because he's going in the opposite side of the goal. Therefore, the uncertainty is high in the top part of the T word, which are places where expected meaning disagree. And that should enable the robot to find out which oracle or which hypothesis is telling the truth. So let's run this example. And as you can see, and as predicted, the data are indeed not labeled the same way for hypothesis 1 and hypothesis 2. That means the oracles disagree. But the probability of each hypothesis did not evolve. Both hypotheses are as likely. So it seems active learning techniques based on meaning uncertainty are not well suited for our problems. But why? Well, simply because for both hypotheses, even if the robot interprets the signals in different ways, the signal still makes sense in both cases. Let's say, for example, the user was using two words. So this word, which is situated in this area of the feature space, was dog. And the other word, which was in this area of the feature space, was cat. And so for hypothesis 1, the robot believes that the word dog means wrong, means that the action he did was incorrect, and that cat means good. And in hypothesis 2, it just believes that dogs mean good and cat means wrong. And both makes a lot of sense. So what would you do to disambiguate the hypothesis if you are in these situations? It's simple. You know that you cannot go right and left because you were doing this before and it's not helping, so you can try to go south. And if you go south, indeed you will receive one signal, let's say this signal, and you will label it the same way, because in both cases, the meaning of the signals is wrong. So that will actually be a red point here, and also a red point here. And you can see now that the nice structure of the data is broken. And if this example happens, you can hypothesize that hypothesis 1 is more likely than hypothesis 2. So that seems to solve the problem, and you could tell me that's easy. If we want the two hypotheses to agree on how to interpret the signals, the robot should perform action where both hypotheses agree on. So let's put this assertion to the test. So we have our toy problem, and the robot will only go south and north, which are actions where both hypotheses agree on the expected meaning. When you go south, you expect a no. When you go north, you expect a yes. So let's run this example. And as predicted, both hypotheses agree on the meaning of the instruction signals. But once again, none of the hypotheses discriminate one from the other. Why? But for the same reason as before, it's kind of obvious. Both interpreted the signal exactly the same way. So both are as likely to be the correct one. So what would you do to differentiate the correct hypothesis? Well, now it seems obvious that you want to take action where both hypotheses disagree on. And this is, for example, by going left. By going left, you will receive one signal, let's say here, and you will assign labels. For hypothesis 1, it will be good, so it will be green. And for hypothesis 2, it will be a bad move because you're going away, so it will be red. And you can see that we broke the nice shape, the nice structure of the data we had before, and we can see that hypothesis 1 in this case is more likely than hypothesis 2. So let's summarize. We have seen two strategies that the robot may choose to differentiate hypotheses. And both alone are not working. At some point, you need to switch from one technique to the other. And the question is there any invariant in both situations? Is there any higher principle that could explain both situations? So let's see. In the case on the left, the optimal action, the correct action to do to discriminate hypothesis was to go south. And if you go south, hypothesis 1 expect to hear something that means no. And according to its current model, a no means a signal in this area of the space. Hypothesis 2 also expect to receive something of meaning no, but according to its current model, no is in this area of the space. Therefore, when we will receive the real signal, it will be either here, but for both hypotheses, it will be at the same location of the feature space. So this way, by looking at the expected signals, we will find out, once we will receive the signal from the teacher, which one were telling the truth, which oracles were telling the truth. And the exact same idea holds for the task agreement case. So in this case, the optimal action were, for example, to go left. And if you go left, hypothesis 1 expect to hear a yes. So he expect a signals in this area of the space. While hypothesis 2 expect to hear a no, because he is going away from the goal. And once again, what we can see is that when we will receive the teacher signal, we will know which one is lying, because they does not expect the same signals. And that is the invariant. In both cases, optimal action is when both hypotheses disagree on the expected signals. The idea is not usual in current research lines and is tightly linked to the kind of problems we are facing here, where both the task and the signal model are unknown at start. To summarize, uncertainty is here about the expected signals that each hypothesis, each oracle would predict. But importantly, this signal still depends on the expected meaning, plus on the signal to meaning model, or meaning to signal model to be more specific. It should be quite clear at this point, this idea of uncertainty about the expected signal, but let me draw a few additional diagrams to convince you of this in another way. So that is the situation of our algorithm. The user is teaching the robot to do whatever he wants him to do using spoken words, which, for example, are feedback on its actions. And those spoken words will be translated to symbolic meanings using classifier. And in our case, we have one classifier for each hypothesis, for each task hypothesis. And importantly, as the robot knows the set of possible actions, it is able to assess its own action as good or bad with respect to each hypothesis. But as for each task we have a different classifier, each meaning may not correspond to the same teaching signals, to the same vocal word in this case. And this is why in the kind of problems we are tackling here, there is an additional layer of uncertainty that is due to the different classifier we train for each task hypothesis. And we understand why now, in more classical scenario, this is no more the case. Indeed, in more standard scenario, if the robot knows the number of possible tasks, it can still assess its own action as good or bad. But as the classifier is the same for all hypotheses, the meaning to signal correspondence is also the same for each task hypothesis. So the robot knows which word is used to mean correct and incorrect. In other words, there is no uncertainty in the classifier. There is only one common classifier, the one trained and tuned by the engineer in this specific setup. Therefore, doing an uncertainty on the signals is equivalent as doing an uncertainty on the meaning. And there is therefore no need to do this step of signal uncertainty. So I hope I convince you at this point that we need to do uncertainty on the signals. So let's see now the example on our toy scenario. So this time the robot is following the rules we defined previously, trying to reduce uncertainty about the expected signals. And you can see the nice behavior of the robot, which is going east-west and north-south iteratively, with the uncertainty map changing with respect to his movement and the structure of the labeled points. And for the first time, you can see that the two hypotheses start to differentiate. Why? Well, you just have to look at the labeled feature space for each hypothesis. In one case, it is perfect. It perfectly explains the structure of the data, while in the second, it's a big mess. So the robot's action allowed to find out which one of the hypotheses were telling the truth. And importantly, this planning strategy should take into account all possible actions in every state of the world, and not only in the current state. The robot should plan several actions ahead in order to reach part of the state space that will help differentiating the hypothesis. It needs to go where there is information, where there is useful information. So we should now test this algorithm in much more complex scenario where there is much more hypothesis and where the feature space is of higher dimensionality. But before starting, I would like to come back to an important point that you may have in mind at this point. The question is why, for every problem, we could not just look for places where hypotheses agree. This way we can create a model of the signals and then run a classifier and use it for a standard learning problem. And that would indeed be one simple way to solve the problem. But there is two arguments against this. First, how would you know when you have enough data to fit a good classifier? When would you shift from one method to the other? And the second argument is that in more complex case, there is no such state where all hypotheses agree. This is a toy scenario. And actually, in all our scenarios, all hypotheses could never agree at the same time. And a quite counterintuitive result is that actually the grid world example is among the most difficult problem you can find, because in literally every state, every action can be interpreted differently for every task hypothesis. So enough theory, let's see how this actually scales to more complex scenario. So our first experiments will consider a puddle world where the robot must reach a particular area, here in red, while avoiding another area, here in blue. The robot can perform 4 different actions, north, south, east, and west. We generated a number of 660 hypotheses composed of all possible combinations of this red and blue area. And here is one other example of a world we can generate with its associated policy. And this policy will be used by the teacher to assess the robot's actions. And you can see that for this policy, which starts from the top left corner, the agent is going around the blue area to go to the red area. And the teacher will once again use spoken words mapped to a 20-dimensional feature space. And as we have seen in previous videos, there is 2 sources of noise, the one from speech itself, because spoken words are never pronounced the same way, and the one more important that come from teaching mistakes, with the user not assessing correctly the action of the robot. As we want to evaluate the performances of our planning method, we will compare it with other methods. We are considering random action selection and epsilon greedy, where the robot is going towards what he believes is currently the correct task. And finally, we will consider 2 uncertainty planning methods. Both of them are about uncertainty for the signals, which is the one we identified as the correct one for our problem. But one will look at all the state space, and the other one will just look one step ahead. And you can see that our planning algorithm perform better than the other methods. While the myopic case is even worse than the random state, because what often happens is that the robot gets stuck in a right, left, or north, south kind of schema. And one thing that is interesting when we have an uncertainty that is defined is to look at this uncertainty map. We show here an example of a particular run. On the left, we plotted the uncertainty map at different time steps, and on the right is the learning curves, with the different time step annotated. In black on the uncertainty map, you can also see the trajectories of the robot after step 30. So for 10 moves, at step 30, the robot is going towards the area of higher uncertainty. In red is very high uncertainty, and in blue it will be low uncertainty. And you can see that the more you progress in the learning, the less there is red on the screen. And once you learn, after 240 iterations, once you know what is the task, then everything is blue. There is no more uncertainty. We further applied our algorithm to the BCI control task we presented in previous video. So this work has been done in collaboration with Iñaki Iturrate and Luis Montesano at the University of Zaragoza in Spain. And we are using here brain signals, and the user should teach the robot to navigate in the grid world by assessing the action of the robot using his mind. Testing several action selection methods will take a lot of time if we want to put real user in front of the system. Therefore, we use the database of recorded brain signals and simulated 400 experiments for each action selection methods we choose to test. And the results are quite impressive. With our method, we allow a new user to teach the robot without any prior calibration of the system in about 70 iterations. It means that you can just pick a subject, put him the EEG cup on his head and start the experiments directly and succeed in less time than it usually takes to calibrate a system. So interestingly, we can see that active method based on meaning uncertainty does not perform very well and even sometimes fails to identify the correct task. And the pure greedy is even worse than that. It just never succeeded at identifying the correct task. And random, interestingly, performed quite well in this setup with 150 iteration on average. We are now at the end of this video, which I think is key for understanding this work. At this point, you should understand the specificity of learning from unlabeled instruction and which kind of action should be performed to optimize the performances of the algorithm. And such action should tend to reduce uncertainty about the expected signals from the teacher. Finally, we demonstrated the performances of our planning method with respect to other methods and shown that it has overall better performances. And in next video, we will discover additional interesting features of our algorithm, from which the most important one is the ability to reuse acquired knowledge to learn faster a new task. Our algorithm is also able to output a confidence on its current understanding of the problem and therefore on its understanding of the teaching signals. And another important aspect is that our approach can be combined with a known source of instruction, and still, the use of unlabeled signals may improve the performances. From another perspective, even if it was not explicit, all the scenarios we considered in this work were solved using reinforcement learning techniques to compute the policy associated to each task hypothesis. So we are not restricted to the use of reinforcement learning techniques. In fact, our algorithm only needs to be able to assess its action, whatever the method you may want to use. And finally, we will see how we can still learn a task if the teacher is using both feedback and guidance instructions during the same interaction session. And this case is very particular. It's very complicated because the teacher can only send one instruction per iteration, which means the robot doesn't know if each received signal will be about the action it just did before or will be about the action he will do in the future. Thanks for watching and see you on next video.